because this is going to be probably the first like 3 classes into 12. And I just want to make sure I know everything in those 3 classes before I even take a step in. So last time we were doing this, the directional derivative, I didn't finish it. I realized I made a mistake, which is why I had to redo it. So directional derivative is this process over here where we have df, dn, and turning that into a dot product. And we get where the sensibility comes in. This n is direction, while this k, and this is the vector. So if you think about it, what is in this? This is equal to delta f divided by delta x, and so on. With the dot product of the vector, what you're doing is saying we have a direction. We have a direction I, j, k. Let's just say this for the direction. We're taking dot product, so we're saying f x1 goes into this direction, so forth, so forth. It makes sense. You're kind of getting a format over here. The partial derivatives is always kind of like directional, like this, right? If you look at that, it makes sense. But looking back at the form we got after using the stroke hole, which will get you this form, I believe it was this dot. Was it right? I think I'm right. Was it? Yes. No. Yes. This v equals 0, and over here we get a vector term, and we get the negative p plus the we don't get that. We get the f term with the density, not the that one. And over here, obviously, we get the full. No, we get the this dot density v equals 0. Now, where I think that's right. Yes, there's a density here. Now we divide density everywhere to get that form. And over here, I think I did this wrong. This goes away. Okay, so this goes into v squared divided by 2 gradient parentheses, right? Remember correctly? Plus v cross gradient cross the v, right? That's what we got. Equal negative gradient p divided by density plus density goes away, f prime, right? And with that, we move our up, and then we make this into a negative gradient u. Okay, and then we move this here, so gradient v squared divided by 2 plus u, and then we have plus v cross v, and then equal negative p over density, right? And now we do something interesting. We do a v bar, we do a v bar dot v, we do a dot product here, and we do a dot product again over here, and again over here. Now, what does that do? Obviously, this turns into our perfect L equation. So we get v squared divided by 2 plus u. Now, this over here is interesting. We did v dot v. This is vorticity, like this, just to make it easier for us to see. And then we have p times density, and then we have v bar divided by v absolute, but absolute. Okay, what does that tell me? Is the question. Okay, so I'll put the plus sign over here too. Now look over here. If this is the velocity direction, let's just assume that's the random v. Okay, and then this vorticity is this direction. We get a 90-degree from here, right? Now this over here is a unit vector 2 over here. This unit vector over here. What's that? That's a 90 degrees. So the dot product of that is null. That's it. I explained everything to you about this topic. It's just null. With that said, we are moving on, I think. Are we done with this stuff? I think we are. And I already explained why this is true. And everything is cha-ching. Okay. We're moving on to here. That may be different for different streamline. Okay, yeah, sure. So then this last result can be simplified to describe a steady flow of a large Reynolds number using the definition of entropy. Okay. So what is saying, again, is how did he get it? We'll figure it out. And then we can simplify it to 1.31. 1.1 is over here. Okay, I can understand what he's doing now. Okay. So we start with d ds equal dh minus dp divided by density. So this, let me just really quickly use. We're going to move this here way far away so we can actually use this later. Yeah, we're almost done with this chapter. As you can see, the last few things of this already, the copy of this. Okay. We'll do this real quick, really fast. Now we know that S ds, this is just a constant, so this can go to 0. 0 equal dH minus dP small. So again, we continue over here. We multiply by density here. So we see that dP equal dH like this, right? Now what he's doing is basically adding a dl. There's nothing special about this other than doing that. And then we're good. So this part is done. Now, with that said, we have this property over here that relates us from pressure to entropy. Now, this is important because we can go over here to the original denotation. See if I can do it from my head, which I probably can, or because it's just a convective term, equal a negative gradient P divided by, I believe it was density, right? And then it was, it was plus, I believe, minus gradient U, right? And that's what it says. And it's 1.32 he wants to copy. So this version of it, okay, so not the other version. So as we'll do this again, which is gradient of v squared divided by 2 plus v cross the v cross v gradient, so on, equal negative gradient p divided by density minus gradient q. And then this will give you parentheses delta dl, right? Parentheses, let me just shortcut this a little bit. We got that from here, and I remember we got that from here. And I remember we got this over here, which was separate from these two. So it was delta p over delta l. I believe it had a density, and everything else is 0. Am I correct? Okay, we go. And then from this portion over here, we can see that this needs to be worked on, which is given by this relationship over here. So we can then add that this is density divided by density L, v squared divided by 2 plus u. And then we can add this into here, which is going to be plus h. Now, why can we do that? Look over here, add in our 1 divided by density, parentheses density, dh, dl, and then we have it. We get dh, dl. And then dh, dl can be subbed into here. That must equal 0. What does that mean? It basically means when S equals SO, we have a relationship of all these SOs. I'm pretty sure. That's my take on it. I'm pretty sure that's what it means, but I'm 98% sure that's what it means. Otherwise, nothing. Why would he do that?